Read the chat.
Then I would invite Garrett. Are you there? Yes,
I am.
Yeah, good morning.
Good morning.
So Garrett is the founder of Windfisher from France, and he will tell us about the Magnus effect balloons for distributed wind energy. And I guess you will need to give us a little bit of explanation because not all of us are experts in this topic. So
I'll try to do that today. Can you see my screen okay?
Yes.
With the presentation?
Yes.
All right, perfect. So yeah, good morning, everybody. Very early morning to Mike Berging and the Americans over there. My name is Garrett Smith, and I'm the founder and president of Windfisher. Our company is developing a decentralized renewable energy system, which is twice as productive as solar PV at half the price of competing systems. And this is all thanks to our disruptive cylindrical winged Magnus effect kites. What our objective to do is to develop a containerized system which provides wind power in a box. We have everything shipped to the site inside the container, and then we're going to unroll the balloons that we're going to put the structural elements to and inflate them, and then be able to deploy it and commission the system quickly and easily, even on unimproved sites. So I'm not sure if, I think we've had some airborne wind energy presentations in the past at this conference. The key premise we have for airborne wind energy is that we're able to go higher at higher altitudes of 50 to 500 meters, where the winds are stronger, more persistent, and therefore we have more power available in the wind. And the reason we can reach these altitudes is because we have a lightweight kite, which is linked by structural cables to the ground station. And those structural cables mechanically transmit wind power to the generators that are at ground level. And here on the right, you can go ahead and see our very first flight test back in August of last year, which was one of the, the very first one we actually got up in the air. Very simple concept, about 500 watt power equivalent. So the big thing that we're trying to do is we're trying to fill the gaps of the decentralized energy pain points. And, as you know, the diesel and the batteries, they're dispatchable, but they're quite expensive today. Wind and solar is intermittent, even if it is cost effective. And so we're trying to really bring that to a different level. And so we're at least 2 times more productive than wind and solar. We can get up to capacity factors around 55%, depending on where we install the system. And we're targeting half the cost of wind energy for a comparably sized wind system. And the reason we can do that is because we're getting roughly twice the energy because of the increased hub height that we have. So here's a video that kind of gives you an overview of how it's going to work. All right, and I'll be happy to show that again at the end if anybody wants a replay. No, let's go down. Not right now. Okay. And so our initial product offer, what we're looking at is we're looking at diverse sizes of kite systems as far as the power rating. So 5 kilowatt, 35 kilowatt, 100, and 500. And one of the key things about this is once we get to a certain minimum size, a minimum wingspan, which also influences the volume, we're able to inflate them with helium so they become lighter than air. And so that transition point is right around 100 kilowatts. And that allows us to keep our kites up in the air all the time, ready to produce energy whenever the wind is blowing. And we don't have to do the launch process. So our capacity factors at 6 meters per second are around 55% for these larger systems. We're going to be starting around 100 meters altitude for the smaller systems and trying to get up to 200 meters for our large systems. And as you can see, our 5 kilowatt system has a wingspan of 6 meters, and we go all the way to 45 meter wingspan once we're at the 500 kilowatt. So here we have to explain our performance and to give you a better idea of where we see the advantage, and then with the power curves and the overall performance. So on the left is we have a power curve comparison, and because of the design, we're actually reaching our rated power at about 6 meters per second, and that's this whole area underneath this power curve is where we get the majority of our energy increase compared to horizontal axis wind turbines. And we're comparing it to a horizontal axis wind turbine that has 9 meters per second. But then you'll see that we start to drop down. And the reason we drop down as far as the power production as the wind speed gets better is because we have a cycle where we're letting the kite go out, and then we're bringing it back in this retraction phase. As the wind increases, we have more drag on the kite as we're bringing it back to its starting point. On the right-hand side, you'll see that if we go up to the 6 and 7 meters per second, we're getting 3 times the energy production. But then we drop down and we're only, when we do the whole Weibull curve up to 25 meters per second, we're getting an advantage of about 1.7 times. And the key thing on the energy is that there's more frequent winds at the lower wind speed than the higher wind speed, and that gives us the big benefit. And here you'll see that we have our 55% capacity factor versus an ideal Betz limit turbine at just over 30%. So I've installed a system at Folkecenter virtually. Here you can see that on the picture on the left. That's a satellite view of this Folkecenter. And we need to have an unoccupied operational volume of 300 meters radius. And that includes a 50-meter safety buffer. It doesn't prevent using the land that's underneath, but we do in the initial stages need to have this land free of human occupation while we're in our early operation phases, until we have a proven track record, until we get the appropriate certifications. And so what we do is, if we have people that need to get to this area, we'll land the kite on the ground station, and then we'll launch it at a future time. And on the right-hand side, you kind of see this volume where our ideal operating altitude is 100 to 125 meters. And that gives us a kind of an elevation angle of about 20 degrees. And that angle can actually change depending on the wind shear profile and the wind speed to really target the maximum benefit, the optimal extraction of the wind power for harvesting. And so now you're going to get to see some real testing. This is our twin cylinder Magnus effect kite, which is flying figure-8 crosswind patterns. It is at a fixed distance. We don't yet have it going on the cycle, but that's because we're using this as a test platform to generate our aerodynamic data, so we can plug that back into our simulations and use it for increasing our understanding of the system and redesigning it for the next steps along the ways. On the simulation side, you'll see that for 100 kilowatt rated power, our latest simulation is showing a cycle power of 68 kilowatts. So right now we're about 70% of performance of what we want to be. And we do have ideas for how to improve that and get that back up to the 100 kilowatt rated power. But you'll also see that the peak power is higher than the rated power. And what we're using as rated power is we're using the cycle average at the rated wind speed to give our rated power, but we need to have some excess power for both generation and retraction. And you'll see here on the peaks on the retraction phase, those are still artifacts of our very basic control strategy that we've implemented at this early stage. And we're confident that we're going to be able to smooth those out and get to something that is actually robust for the system. On the aerodynamic side, we are able to extract some data. You can see that this lift coefficient curve is actually quite consistent and smooth. And however, on the drag coefficient, you can see that we're kind of all over the place. That's because our onboard systems are not yet performing at the level that we need to get precise results. We're in the process of developing a second generation data capture system that we'll be implementing here this fall. And that will allow us to get much more precise aerodynamic data, whether it's the lift or the drag coefficients or the other coefficients that we're interested in. As far as our roadmap, we were founded back in June of 2021. We applied for our first patent. We were able to do our first flight testing. And then this year, we were able to go into the towed testing, where we had it on the top of my car and dragged it down the road to be able to generate the wind speeds that we need. We've received public funding of 238,000 euros so far. And we're now entering our fundraising round, an equity fundraising round for 500,000, which will be matched by another 500,000 of public funding to take us to the next level of maturity. And that includes more numerical simulations, the design and build of our proof of concept at 5 kilowatts. And it will also include the specification of our 100 kilowatt system. Once we get to that stage, then we're going to need another 5 million in seed funding to design and build the 100 kilowatt system, which will be lighter than air. And that will also help us to drive the industrial ramp up and get to the stage where we can actually have a full test campaign, including autonomous operations. As far as letters of interest, we have a few in the industry. Enerware, they're based in the Middle East, and they're looking to use airborne wind energy systems and be one of the first ones in the region to actually deploy and operate one to help furnish or to provide energy to their mini grids, which currently are using solar power, diesel power, and a little bit of batteries. The wind that they have there is actually offset from the solar PV profile. And so from early afternoon until the early morning hours, if they were able to deploy an airborne wind energy system, they could actually reduce their diesel consumption and get from 25 to 30% renewables up to 75, 80. They'll never be able to get rid of their diesel generators entirely, but it really helps improve the penetration for the system where they're supplying energy to individual companies. For Engie, they're a big operator of traditional wind turbine farms. They're looking for a green genset, so something that our container that we can bring onto their site, produce power for them for typically a year and a half while they're constructing their wind turbines and commissioning their site. And we all know that on a wind turbine site, we have lots of wind already, and we've got lots of space. So our system will be able to go in there and actually be installed pretty easily and temporarily. And then they'll be able to move it after the commissioning of their wind farm to a new site where they're constructing, where they're beginning construction on a new one. And we can also work in the maritime propulsion industry. Farwind has a concept using Magnus effect sails to drive their power boats, the power ships forward. And so we're basically proposing that we can use the Magnus effect kite to go higher altitude, get better wind, and pull their ships through the ocean. We're also supported quite well by the local ecosystem here in Grenoble in France with Tarmac Incubator, BPI France, which was one of the public funding agencies here in France, and then a couple of the smaller local ones, whether it's the region, Auvergne-Rhône-Alpes, or Initiative Président Isère, which is a local community. So basically, before I answer your questions, I'd like to ask a couple of my own. How can you help push this innovative new technology forward? And then I'd like to also get your insight into who needs this system now, who might be able to collaborate on R&D, and who can help finance the technology development. Thank you very much. And I'm available to answer any questions for you.
Any questions? Not now.
No, I need.
Thank you. So is there any question from the audience?
100.
Very simulations.
Yes.
So I have one.
Yeah. Okay.
Yeah, sure.
Yeah. Tell me what about the wire during the go and back?
Can I talk about the what? The what?
The wire.
Wiring system.
The wiring.
Okay, so we have no copper wiring. We have no electrical wiring going from the kite to the. Just a second. Let me get something else.
I'm not talking about the copper wire. The tension wire.
Not production wire.
You're talking from the wiring from the container to the grid, or you're talking?
No, the one that connects it to the ground.
Yes, this
Okay.
one.
Yeah.
So here you can see our little mock-up.
Yes.
And so we've got the two cylinders up here, and these are mechanical cables.
Yeah.
And so basically the system has the mechanical cables go around the kite, and we have 4 winches in the ground station. So that allows it to manage the distance away from the ground station, as well as the rotational speed of our cylinders.
Okay.
Yeah. So you depends on the wire to make a rotation. That's right. The rotation for this tension wire to make a rotation for the generator on the land. That's right.
I didn't understand the question about the.
Maybe you can come here and see you.
I'm having it's a little bit
Yeah,
challenging. to
just
hear.
come closer to the microphone. What's up,
Yeah.
table?
Yeah.
And you can see also the face.
Thank you.
Yeah, welcome. Thank you. It's very, very good presentation, and it's very, very good idea. I'm admired with this idea. So I want to ask you about the tension wire. You have a floating helium balloon, and it will make a tension due to the wind. So the wires that catching this balloon, it will make a rotation for the generator on the land. That's right.
Correct. As we pull out, as the lift force is managed for high lift force during the generating phase, we're pulling out on the cables, which are turning the winches and the generators in the ground station. And at the same simultaneously, we have a different speed between the two sides that are actually rotating the cylinders.
Yeah.
And that's how we're basically tuning the wing to the wind speed to optimize, to maximize the wind force, the traction force.
Yeah.
And then we reduce the speed when we want to bring it back in, so the wings are not spinning very fast, and we're pulling them back in to start with a low drag force.
Yeah, this is elastic wire or not elastic. You will call it flexible to pull and push, and the white cylinder you are in your hand, it rotates itself.
No, it's the actual the management of the cables.
Yeah,
creates the rotation.
Yeah, it make a rotation. This one will make the rotation for the generator.
The rotation is not driving the cables. The force is driving the winches, which then drives the rotation. Yeah.
So the generator depends on the movement of the cylinder itself and the wire, or depends on the rotation of the white cylinder.
No, the generators depends on the force, and the difference between the generators and the ground station allow us to manage the rotational speed, which then influences the force.
Yeah. So you are depending on the force of the wind for moving it far. But usually if I have a floating balloon, usually it make a tension. During I was a child or kids, my balloon usually make a tension. how can it will back again? This is if the wind speed becomes slower, so it will come back.
It's because of the speed of rotation. The faster we go, the higher traction force we have.
Yeah.
And then we slow it down, and that means it's easier to pull it back in.
Yeah.
So maybe what I can do is I can put a link to our technical paper in the chat, because we presented a technical paper at the Airborne Wind Energy Conference in Milano in June, and maybe that'll help get some understanding of how it works as well.
Very interesting.
Yeah. Another question: if the wind speed is higher, so the balloon go and will make a tension for a long time. No, nothing for the energy will become, because the balloon will go and it will make a tension for a long time. You will use this energy for rotating anything.
Now, once we get to the limit, we have to bring it back in, and over 25 meters per second, we're going to be storing the system. We're going to be landing the system and securing it to the ground station, so that it doesn't blow away, that we don't over stress the wing or the cables.
Yeah. But in case of the wind speed, the high wind speed, it will take the balloon and go and stay for this position. It need more wire to go far.
Yeah, but once we get to the end of the wire,
yes, at the maximum tension.
Distance, yes.
What about the motion on the generator or the forces?
It's just drag then. Once you get to the maximum, it would no longer be rotating then in that case. But yeah, I suggest if you want, you can give me a chat. You've got my phone number. There was my phone number. I can put it back up on the screen.
Okay, I'll send you my contacts to send me some presentation, and I have to see you and to discuss this good idea. I think it will be good for the wind future in the world.
Very good, very good. Yeah, please give me a contact. So there's my contact information back up on the screen. You can write that down.
Will you share the presentation afterwards? Or anyway, yeah, we are recording, so
yeah, you've got it recording, so that's not a problem. It's online with the recording, and anybody can access it afterwards.
Perfect. And I also have a question concerning the wiring system, because when I talk to other people working with airborne technology, one of the things is like they don't really know what happened with birds. And we know in the wind industry that the bird topic, it's a little bit of a taboo, because that's many people will say, wind turbines kill birds and so on. True it or not true, but yeah, last time I spoke with someone from the airborne industry, they said, we don't really know how to handle the problem. Has there been any thought in this direction?
So to be straightforward, no, we haven't studied that. We know that that's one of the things that needs to be done in the future. But we do believe we have an advantage over profiled, typical gliders style wings. And the reason for that is that they're flying at 80 to 100 meters per second, and we're flying at 15 to 20 meters per second. So we're flying at 1/5 the wind speed. And that's because the Magnus effect has a very high lift coefficient, which still allows us to extract a lot of energy from our system, but we're not flying nearly as fast. So that gives birds more time to evade our system, and we also have less energy in the event of an impact.
And one last question from my side. Are you planning to set up the system only as like in flatland, let's say, or also on the top of mountains? Because in many countries you have wind turbines up to a certain size that are covering the whole mountain surface, and there has been a lot of discussion on that, of course.
Yeah, any site that has decent wind, initially we're targeting the lower wind sites because that's where our advantage is versus conventional wind turbines. We can put it on the top of the mountain, we can put it down lower. As long as there's wind, we'll be able to extract that. And here in Grenoble, we're in the Alps, where there are several areas that have daily wind cycles. We could actually put this thing on the side of the mountain, kind of oriented where it takes advantage of the vertical thermals and not just the horizontal wind on a flat land.
Okay, thank you. Yeah, one more.
That's the question from my side. The rotating 4 cylinders, do they have energy storage? Do you store energy within half I omega square with the rotation?
Our system
Are you
currently
storing
has
some energy in them? And their speed?
our system currently has no dedicated energy storage. So we do have the peak power production and peak power consumption. We are looking at how to smooth that out. There is no energy storage up on the flying parts, but we may have a smoothing system down in the ground station.
Because actually wind is not constant, and sometimes you can store energy and your flywheel to absorb the change in wind movement. So these cylinders have certain inertia and they have certain rotational speed, then you can store mechanical energy in them as inertia storage. Half I omega square.
There's a very minimal amount because our system is actually very lightweight. It's just, aerospace textiles and lightweight structure. So there's not a lot of mass to store the inertial energy in the cylinders.
What type of generator you have in the ground?
Right now, it's just we're working with electrical motors, motor generators. We haven't made a specific choice yet for our final architecture.
I guess it's also a work in progress because at the end it's a quite new sector that you are working on.
Yes.
So many things still to solve and see. But it looks, I saw this concept first. I think it was 4 years ago in Hamburg, and since then I could see that more and more companies started to appear. So it looks like something is going in the right direction. Yep.
No, we're all making progress, and we have. There has not yet been a consolidation on a specific technology. The wind industry is 3 blades, horizontal axis. That's kind of the standard default. In airborne wind energy, we haven't yet reached that phase. All right. Well, feel free to reach out to me and give me an email or a call at any time, and I'll be happy to answer any more questions offline.
Perfect. Thank you very much for the presentation.
Thanks.
So now I just noticed that I wrote in the program 11:15. The next one is actually 10:50, but I guess people will understand it that there were 2 11:15s at the same time. Anyway, before that there is a break. So we have 25 minutes of break basically, just to stretch out and get some coffee. And for those who are on the other side of the world, maybe have a short nap. And then we will continue after the break, so at 10:50, with a quite interesting concept, because it's a way that we can turn existing solutions into modern life applications. But I will not spoil the topic more. So have a good break. The meeting here will remain on. I will just stop the recording during the break, of course. And see you in 25 minutes.